So hello everyone, uh, I'm Bhrigrishi Mishra, PhD student at IIT Bombay, and I'm one of the TA of this course named as Elements of Solar Energy Conversion. So there will be two online interactive sessions, one with me on each Friday at 6 to 7 p.m. and one with the other TA from each Saturday 6 to 7 p.m. So this is the first online interaction session. So I hope you all have gone through the lecture videos which was already published. Now I think second week video is also there in the portal. So I'm assuming that you guys have gone through the videos. So we'll start with the week one. So before going to the content, so I have something for you guys, like why like the current India's energy consumption. So if we see uh, this so coal and hydro, sorry, coal and oil, these two have maximum share 56 and 29%, which sums up around 85%, and little around 6% of gas, so which is basically natural gas resources. So but these are the limited resources. So 56, 29, 6%, so these are like sums up 91%. So currently this is the data of 2017. So India's primary energy consumption in 2017. So if so based on this data, we can say that 91% of India's energy consumption comes from the non-renewable resources. That is the resources which are limited. Like there will be a time when we don't have any these resources. Like they will be empty. So that is why it is called non-renewable resources. We can't renew them. Okay. So okay, that is the one thing, but like this is the course of elements of solar energy conversion. So what is the need of solar energy? Why do we want to study solar energy? uh, so like first of all, 91% only from the non renewable energy resources, but okay, that is fine if they are limited. But what are the things that we are getting from those by using those non renewable resources? I mean, is it good for our environment or not? So if we see the stats, we all know like there is a lot of problem with fossil fuels. As we have already seen, 56% only from coal, and coal is the primary energy source for electricity production in India. So there is a lot of problem with fossil fuels. For example, like these are the certain impacts which is included here. Ocean acidification, extreme weather, we have seen like irregularity in the weather. Like currently in India, lot of heat waves are there, temperature gone to very high. And even if we see, there is an article which states March is the new May, because in March even the temperature rise up to 40 or in close to 45 in some part of India, especially in the northern region. So this extreme weather, in one part of, I'm talking about India, but this is the scenario of the whole world. In one part, lot of like heavy rainfall. In another part, hardly there is any rain. We have also seen lot of news about sea level is rising, and then plastic pollution. Lot of if you see lot of like plastic we have found from the ocean itself. Okay, air pollution, this is one of the major problem which we are facing right now because of use of fossil fuels. Burning fossil fuels produces lot of CO2 emissions, and which again emit PM 2.5, PM 10, particulate matter which size is around 2.5 micron or 10 micron. So these are very which has several health impacts to humans. Then again, water pollution, there is water scarcity in lot of regions, like in Maharashtra, in Rajasthan, lot of places water scarcity is there, and apart from that, water is also polluted. Oil spills, so you might have seen lot of news of oil spills in the ocean. And then, yeah, as we talked about health issues, so there are n number of problems because of the use of fossil fuels or non-renewable resources. And these are not the uh, like uh, uh, one time thing. It is impacting our climate also. If you see this uh, this data, so this compares the temperature with the CO2 CO2 content in the atmosphere. So if you see the temperature and CO2 are proportional to each other. When CO2 rises, the temperature also rises. So this is the case of this bottom one is for the Earth's temperature, and this is for the Antarctica. So in both the cases, whenever CO2 rises, the temperature also rises. And right now today we are at here 400 ppm CO2 concentration. So if you see, if we follow this trend, the Earth's temperature will also increase, severely increase, if this use of the fossil fuels or the current trend follows. So here is the report which says that this is the last IPCC report concluded that by the end of this century we will get to more than 4 degrees centigrade temperature rise above pre-industrial levels. Okay, if we continue on a high emission paths. That is why there are a lot of conventions like Paris Convention, and so we need to adopt renewable resources in order to reduce our carbon footprint. So how fast are CO2 levels rising? See, you can see 35 ppm in 1000 years, and the recent increase is 35 ppm in 17 years. So we need to change the energy scenario, or the energy which we are using right now. So we need clean energy, and that is why we need to adopt the renewable energy sources. So there are lot of renewable energy sources: solar, wind, biomass, geothermal, hydro. So in which so these are the clean energy and abundant in nature. That means we don't need to pay for it. Okay, I mean they are easily available, and we can harness them. And the main reason of this is, one is abundant in nature, and no need to pay for it. And the other thing is, it creates lower carbon emission compared to burning fossil fuels. So that is why we need to adopt renewable energy sources. Now for this course we are talking about solar. So we will stick on the use of solar, or how solar is helpful. So if you talk about solar energy, there are we can categorize application of solar energy in two parts. One is the solar thermal, and other one is the solar electricity. So solar electricity means direct conversion from solar radiation into electricity by using solar photovoltaics. So these are the photovoltaic cell, which are also called solar cell, which used to absorb the solar radiation and then convert the 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 energy into electrons, which give rise to electric current, and then batteries are used to store those things. We will talk about these things in the later section of this course. The other part, but right now solar cells, you see, like government of India is promoting to use solar PV on your rooftop, because uh, I I if we can cover the entire India's third desert with solar panels, we don't we will not have any energy scarcity in future. So uh, uh, that is the calculation source. That means we need to adopt using photovoltaic. The other one is solar thermal. So solar thermal means using solar radiation to generate heat, like to generate heat or store it in the thermal form. So that is what is called solar thermal. So solar thermal has lot of uses in different areas. Even it is used for the passive heating or passive cooling of the houses or the structures, depending upon the architecture of the house. And it also used to heat the water. Like here you can see the solar water heater, uh, and also it can be used for the solar cooking. So there are solar cookers which are designed to cook the food, although they have the limitation, but they are very useful in certain things. Then solar space heating cooling, which is again depending upon the architecture of the building, we can reduce the AC load. Okay, or in the if we need heating, then we need to allow solar radiation to come in the house, like in for so in Ladakh, there are houses built with such kind of a structure which allows solar radiation to come in the house, which give some warm in that cold weather. Then solar thermal electricity from CSP. So another way to generate electricity is from solar thermal. So this is called solar thermal power plant. There are different ways to generate electricity from solar thermal power plant. So what is the idea is, we have this giant mirrors. I mean, there are mirrors in different shapes. You might have heard of it: parabolic dish, Scheffler dish. Okay, we'll study these things in this course. So we have this giant mirrors, which track the position of the solar radiation. So, and whenever solar radiation hits the surface, it reflects to a receiver, where there is a receiver. So for example, this is sun, and this is a mirror. So when solar radiation hits, it reflects to a tower, where some kind of storage material is there. So this reflected heat is used to store in this tower, which is further used to convert water into steam, and then it uses to produce the electricity. Okay, so there are n number of use. Solar desalination. So in Arabic countries, especially in like Israel, which doesn't have any natural water sources, so they use solar desalination to to purify the seawater, to use it for the drinking purpose. So and so solar desalination can be used to purify the water. And then solar air heater. So there are a lot of example of solar thermal. Specifically, solar electricity has some examples, but it is limited. But solar thermal has lot of examples and which we can use in our daily life. So in the week one of this course, there were two lectures, lecture 1 and lecture 2. In lecture 1, the basics were covered, like introduction of the course, sun as a source of radiation, spectral distribution of EM radiation, solar radiation, what is solar radiation, description of the sun, and sun as a black body emitter. Okay, in lecture 2, the sun earth relationship and extraterrestrial radiation and how the season changes, that those things were discussed. So as I already told, there are two PMRFs for two online sessions will be held for this course, one at Friday 6 to 7 p.m. and one at Saturday 6 to 7 p.m. So for this online session, I am covering the lecture 1, and tomorrow the other guy, Mr. Pawan, will cover the lecture 2. So we will talk about some basic questions, since there are not very much numerical problems in this, since it is an introductory lecture. So we will discuss about some fundamental questions based on this lecture, and also if you have any doubt related to the questions or with the lecture, you can ask. So and these questions will help you to solve the assignments. So yeah, definitely if you have any questions, you can ask. So for example, so problem 1, does solar radiation require any medium to travel? So if you see the history of this thing, so earlier it was assumed that there is some medium available present in the outer space, which helps to uh, uh, give passage to the solar radiation. It is based on, since at the early it was assumed that solar radiation is in a wave form, so like sound wave or acoustic wave require any medium, so this solar radiation also require any medium to travel. But in the later stage, it was practically shown that solar radiation or the EM radiation can also sorry, I'm using EM radiation now, which we'll cover later also. But yeah, so it was seen that solar radiation can also travel in vacuum. So then this hypothesis that there is ether medium exist in the outer space was cancelled. So does solar radiation require any medium to travel? So answer is no. It doesn't require any medium to travel. It can travel in vacuum or in any medium. So solar radiation shows wave nature, particle nature, or both the nature, or neither wave nor particle nature. So um, again, if we go to the history, and at the very starting, the Fermat, you might have studied Fermat's principle. So Fermat gave theory that light travels in the shortest path. So so that means if there are if from one point to two point, there are a lot of paths from which light can travel. So it always follows the shortest path. Okay, from where the origin of ray optics. Okay, then later in the same century, Huygens said that no, like he said that solar radiation or light follows wave nature. So wave nature means it has, or it must have uh, wavelength as well as phase. So wave means it is going like that. So like the common example is if you take a rope and then swing it, so it goes like this. So that is the wave form. So the I can also extend it like this. So this, the distance between two peaks is called the wavelength, and the the phase means either it is going up or going down, that is called the phase. So if I have two waves like this, then I can say these two waves have a phase difference of 90 degree, like this one at top and this one at the bottom. So these has phase difference. So Higgins said that light is light follows wave nature, but then at the early 90s, like 1900 century, so Planck said that light absorb or emit in a fixed amount of energy, that is called quanta. Einstein also suggested with the photoelectric effect. So then it was considered that light has the wave particle duality. That means it follows both wave nature and particle nature. That is option C is correct. So solar radiation is nothing but electromagnetic radiation, only X-rays, only radio waves, or UV and visible light only. So it was first Maxwell who said that solar radiation is nothing but an electromagnetic radiation or electromagnetic wave. So if you see, like earlier Huygens said that it is wave, it shows wave nature, and then in 1900 Planck and Einstein said no, it also follows the particle nature, so wave particle duality. But in 1800 or so, Maxwell proved that solar radiation is electromagnetic radiation. So if like as we have discussed, Huygens said that solar radiation has the wave nature. So the wave equation is like del 2y equals to 1 by v square del 2y by del t square. Here v is the velocity, okay, and y can be some property of the of the uh, of the wave. So when Maxwell derived the equation, so comes out del 2 equals to mu naught epsilon naught del 2 by del t, where this mu naught is the permeability of free space and epsilon naught is the permittivity of free space. Permeability of free space. Free space means vacuum. We are talking about vacuum, or you can also say air, because air has a refractive index 1, and epsilon naught is the permittivity of free space. So if we come, since it was suggested that it is also a wave equation, and if we compare these two wave equations, it comes out that v equals to 1 by root mu naught epsilon naught, and if you calculate the value, it comes out 2.99 into 10 to the power 8, which is nothing but equals to c, speed of light. And thus Maxwell shows that solar radiation is nothing but the electromagnetic radiation. So after that it is called the electromagnetic radiation, and it has a very broad spectrum, which already covered in the lecture. So so now the question is how electromagnetic waves are formed. So there are four options, like electric field from one source interacts with electric field from another source, or magnetic field from one source interacts with magnetic field from another source, or the option C is electric field comes in contact with a magnetic field, or all of the above are true. So since as name suggests, it is electro plus magnetic, so that means it is a combination of electric and magnetic field. So the correct option is electric field comes in contact with the magnetic field, and then electromagnetic waves are produced. So now what is the wavelength range of solar spectrum? So like 300 nanometer to 3000 nanometer, 100 nanometer to 3000, or 100 nanometer to 1 millimeter. So the solar spectrum has a very broad range, although in earth it comes in a different range, but the actual spectrum is around 100 nanometer to 1 millimeter. Okay, that is the entire solar spectrum. So the right option is option C. So which part of solar spectrum is utilized for heat or electricity generation? So we earlier talked about there are two parts, solar thermal and solar photovoltaic. So solar thermal, solar photovoltaic. So solar thermal requires some material to absorb heat. The simple example is water heating. So water has to absorb solar radiation to increase its temperature. So of course, like UV, there is a small portion of UV which also comes to the earth. So UV is there, and mostly it is visible. Okay, visible part which we already seen, it is used for the heat or electricity generation, but near infrared portion is also considered. Like if we see the spectrum, it is like this. So so this is 0.4 and this is around 2. So this is the uh, energy spectrum. So you can see all these energies are utilized in some form, especially visible and near infrared region. So like for example, solar cell, silicon solar cell has a band gap so it requires around 1100 nanometer uh, radiation to produce electrons. I forgot the exact number, it is around 1100 nanometer. Now there is a research going on to produce low band gap solar photovoltaic, so that they can also absorb very low energy which comes in this region, which is called the infrared region or near infrared region. So we also want to utilize this energy which has, I mean, which has significant amount of energy, but it is not utilized very much. So the correct answer is UV, because some part of UV comes to earth and it is utilized and mostly visible, and some near infrared, but these three are considered uh, to produce heat or electricity. So the right option is option C. So now what is the wavelength range of visible and near infrared? So so as I have drawn here, I'll draw it again. So this is for example 0.4, 0.6, 0.8, 1, 1.2, 1.4, 1.6, 1.8, 2, sorry, it's 2, 2.2, 2.4, and so on. And here the energy is 400, 800, 1200, 1600, 2000, 24,000. So this is spectral irradiance. Spectral irradiance in watt per meter square per micrometer, and this portion is the wavelength in micrometer. So if you say the the visible is from So if we characterize this from around 150 nanometer to sorry, this is point 0.4, this is point 0.4, so around this portion, okay, this is small portion is UV, and from 0.38 to point I think I have drawn wrong peak, let me just correct it. So it's like that. Okay, so the peak is around around 0.7 here. Okay, so yeah, so till 0.38, okay, till 0.38 or 380 nanometer it is UV. From 0.38, that is 380 nanometer, to 720 nanometer it is visible. And there are two reasons, okay. One is called the near infrared region and one is called the far infrared region. So near infrared region has the high energy compared to the far infrared region. As we can see, this is the solar spectral irradiance, which gives the energy. So as the wavelength increases, the energy containing in that photon decreases. Okay, so this region is called the around 720 to 1500 nanometer. This is called the near infrared region. Okay, and the rest till 100 nanometer, like I told that the solar spectrum has a range of 100 nanometer, 100 nanometer to 1 millimeter. So from this 1500 to 1 millimeter, that is called the far infrared region, where there are separate radio waves, microwaves, there are lot of things. But these two regions, visible, near infrared region and UV, these three are important. So visible is from 0.38 or 380 nanometer to 720 nanometer. Visible comprises the color, so starting from the violet and go to red. So violet has a color of wavelength of 380 nanometer, and red has 720 or 660 to 720. There is a range. Okay, it's not a single wavelength, but like as we go from lower wavelength to higher wavelength, the color changes, but the overall contrast is in the red form. Okay, so violet start from 380 nanometer and red is 720. So from 380 to 720 it is visible, and 720 to 1500 nanometer it is near infrared, which is also called NIR, and after 1500 it is the far infrared region. But after visible, one thing is clear: after visible, the entire region is called the IR region, infrared, and in that infrared it is characterized near infrared and far infrared. And near infrared is used to produce energy, to produce heat or electricity. Okay, and if I talk about UV, okay, so UV also has three spectrum. So UV A, B, C, it is in reverse order. Okay, so I think I have written somewhere, just a minute. So yeah, so it is in reverse order. It's like UVC, B and A. So C has a shorter wavelength. Okay, so the wavelength increases in this direction. C has a lower wavelength, B has higher wavelength compared to C, and then A has higher wavelength compared to B and C. Okay, uh, increase in wavelength. So this C and B are very harmful, so it is absorbed by the ozone layer, absorbed by ozone layer. Some part of B, UVB, transmitted by the ozone layer, and mostly UVA is also transmitted by the ozone layer. So UVA is comprises from 250 nanometer to 380 nanometer. So UVA is from 250 nanometer to 380 nanometer. That is why so that is why you have so if you see in the literature, so solar spectrum, so generally the solar spectrum, if you see in energy books, so solar spectrum is people have said 300 nanometer to 3000 nanometer, uh, which is used for the energy application, and which has the highest or significant energy. But in other textbook, the range is mentioned from 250 nanometer to 3000 nanometer, because of this UVA part, because UVA is starting from 250 nanometer to 380 nanometer. Okay, now the question is, what are the approximate energy shares of UV, visible and IR in solar spectrum? So if I again draw it like this, so this 0.4, this is UV, and then again this 0.72 is visible. So this is UV, this is visible, and this is uh, infrared region, IR. So UV of course has a very less amount compared to visible and IR. So UV, if we calculate the area of this energy, or if you have seen in lecture 2, there is a formula given to calculate the energy ratio of certain region. So from that you can easily calculate that UV has 7%. Somewhere in the literature, it 5 to 6 or 4% is also mentioned, but generally UV's ratio is varies from 4 to 8%, depending upon the calculation or the range which we are considering. And visible has 44% and IR is 49%. So IR has the most significant percentage, and IR is also responsible for the heating purpose. That is why there are a lot of coatings. If you see the paint, like white paint, so they reflect visible radiation as well as infrared radiation to avoid heating, because if you reflect this visible radiation and allow the IR radiation to come, then it will heat up the structure or your house. So if you want to cool down your house, you need a paint with high reflectivity, solar reflectivity, in visible as well as in infrared or near infrared region. Okay, and if you want solar heating, then you need to allow uh, the structure to absorb visible as well as IR, because only visible will not give you a very high temperature rise. So if you have visible and IR both, then the temperature will rise significantly, depending upon the material which you are using for the application. Now, what are the properties of sun as a black body? So we consider sun as a black body with a temperature of 5772 Kelvin. So if you see the black body, you will see in the later lectures that what is the formula to calculate the energy emitted by a black body, and why and how it affects the how like if we consider any material to be black body, what are the properties we need to consider? So there are certain ideal conditions which we consider. Black body is one of them. We compare the absorptivity, emissivity of certain objects or certain bodies with the black body. Okay, so black body, what is black body? As the name suggests, black is the color which absorbs everything. Okay, and white is the color which reflects everything. That is why the color which reflects everything, the if we have a surface which reflect everything, especially if it reflects all visible radiation, it appears white. However, if it absorbs all radiation, it appears to be black. That is why if you see where solar heating is required, black surfaces are used, especially if you get a chance to see solar water heater, then the surface used to absorb the solar radiation is black, because black absorbs all the incident solar radiation. So and according to Kirchhoff's law, uh, so there are two terms. So first of all, there are four radiative properties. I might tell you radiative properties which any objects shows. What are these? Reflectivity, transmissivity, absorptivity, and emissivity. So these are the four radiative properties which every object has. We have all seen that at the very starting of the lecture, that every body every body with a temperature greater than 0 Kelvin radiates some amount of energy. As temperature increases, the the amount of energy radiated by the body increases. But every body, like me, this pencil, or the device I'm using, or you guys, we are all emitting radiation. Okay, with uh, radiation means the energy we are emitting. Okay, in some wavelength, usually in the uh, far infrared region. So around 10 micron or 11 micron wavelength radiation we are emitting right now. Okay, so we all radiate, and since we all radiate, we also absorb, like we absorb some amount of solar radiation. That is why we get vitamin D. And transmissivity, so transmissivity means how much it allows the visible light. Here we are talking about visible thing only, but if you consider the ranges, then different material behave different in different wavelength region. For example, if I consider glass, okay, glass is highly transparent in visible region. That is why we can see through the glass. Okay, glass is highly transparent in visible region, but again it is highly reflective in the in the infrared region or far infrared region. That is why this is this greenhouse gas effect, where so we use glass to not allow thermal radiation to go out. Okay, that is why in most of the solar water heating devices, glass tubes are used to fill the water, because it keeps the energy inside the tube. Okay, it doesn't allow the heat to go out or to interact with the atmosphere. So that is why, depending upon the wavelength you are considering, the property shows different nature. Only these four are the natures: either reflectivity, transmissivity, absorptivity, or emissivity. So every object has some sort of these radiative properties. For example, we are highly reflective for the visible. Okay, but we may be, like for example, x-rays has been done to check our inside the body. So we have some transparency for the x-rays. Okay, but again, like absorptivity, emissivity are again the factors. So according to Kirchhoff law, if two bodies are at same temperature, their absorption and emission are equal. Okay, so absorption equal to emission, but this is only follows when the temperature is same. It's not like earth absorbs solar radiation, so it can also emit energy similar to the sun, like solar radiation. No, it's not like that. So that is why absorption emission is only comparable when the two objects have the same temperature. We will study it in later lectures. These are the some lame things which I'm talking to you. So absorption equals to emission. So if sun is a black body, okay, so for a black body, whatever it is absorbing, it will emit. So absorption equals to emission, and since it is a black body, it will absorb all sorts of radiation, and the transmission will be zero in this case. So transmission 0, reflection 0, and as per Kirchhoff law, absorption equals to emission. So absorption equals to emission equals to 100% and reflection 0%. So the correct answer is option C. Okay, now this is the last question which I have considered here. So what is the distance between sun and earth in terms of suns or earth? Like if I have, so this is for example sun and this is earth, so there might be some, so there is some distance between sun and earth. So if we want to calculate the distance between the sun and earth in terms of sun's diameter, so what is the correct answer? So the distance between the sun and earth is around 1.5 into 10 to the power 11 meter, and the diameter of sun, okay, ds, is around 1.39 into 10 to the power 9 meter, and diameter of earth is around 12.75 into 10 to the power 6 meter. So if we want to convert the distance between earth and sun, we can divide the diameter of sun and diameter of earth to calculate the distance in terms of dia of sun and dia of earth. So if we divide this 1.5 into 10 to the power 11 meter with the diameter of sun, that is 1.39 into 10 to the power 9 meter, it comes around 100 suns. Okay, the almost figure is 100 suns. So that now since in the options earth is also given, so let's check with the earth. So now to check with the earth, we will divide the distance between sun and earth with the diameter of the earth, 12.75 into 10 to the power 6. So this is 1.5 into 10 to the power 11, and if we do the round of 1.275 into 10 to the power 7, so it comes around 10 to the power 4, means 10,000 earth, 10,000 earths. So the correct answer is option A, 100 suns. Okay, so if we put so the distance between sun and earth can be covered by putting 100 suns in between this. Okay, so that is the huge distance. And if we compare the diameter of sun and earth, so let's divide it. So ds by dA, it is equals to 1.39 into 10 to the power 9 divided by 12.75 into 10 to the power 6. It comes up at, so 1.39 divided by 1.275 into 10 to the power 2, 1.1, so around 100 10. Okay, so so earth sun's diameter is 110 times greater than the earth's diameter. Okay, so yeah, this is the way you can calculate the distance, or you can represent it. It's easy to remember because you won't remember, or you may forgot these kind of numbers. So it's easy to remember in this format that the distance between sun and earth is 100 suns away, or the diameter of sun is 110 times greater than the earth's diameter. In this form you can easily remember. So yeah, that's it from my side, because I have only formally written questions for this session. So if you guys have any question, please ask with this lecture, or the lecture 1, the first part of the lecture. You can also write in the chat box. And this video is also recorded, so you can find it in the YouTube channel. I'm sure the NPTEL committee will post the link of the YouTube lecture as well as this material, so those who not able to attend this session can watch the video and also can access the material here. So if you guys don't have any question, we can stop here, and we will meet you guys on next Friday. So if you don't have any question, we will end the session here. So no question. Okay, so I'll end the session here. Thank you very much.